Let's now take a look at floating point multiplication and division. So floating point multiplication is along the same lines as floating point addition and subtraction. A little bit of a difference, nothing much, but floating point division is different. So let's first take a look at floating point multiplication, which is easy. So let me motivate by showing an example in decimal. So let's assume that we have this convention that any decimal significant will be of the form x point some numbers, some digits, and there is basically one digit to the left of the decimal point. So this will actually be 4.0. Can actually redraw that. So this is the convention that we are using. We can multiply two numbers of the type 4.0 times, let's say, 10 to the power minus 4 times 5.0 times 10 to the power minus 5. So what we would do is that first we will multiply the two significants, 4 and 5. So this will give us 20.0. And then what we will do is that we will multiply these two exponent terms. So we'll basically add the exponents and add minus 4 and minus 5. So what we'll get is 20.0 times 10 to the power minus 9. So note that after the multiplication, the result here that was obtained by multiplying the significance is not in the normal form. So to bring it to the normal form, what we can do is that we can do to make it 2.0 times 10 times 10 raised to the power minus 9, which is 2.0 times 10 raised to the power minus 8. So then this comes back to the normal form. So we'll do something very similar with binary numbers over here. So what we'll do is that we'll add the exponents, right? So because there's a multiplication, we'll add the exponents. So recall that the E field is actually the real exponent, right? Plus the bias. So if I then have EA is XA plus bias. Similarly, if I have EB is a real exponent XB plus a bias. So if I add EA plus EB, then the bias will get added twice, and that will definitely be wrong. So the final result that we want is XA plus XB plus bias. But since EA plus EB will add the bias twice, what we do is we add EA and EB and then subtract the bias. So then the final result that we'll get is essentially the sum of the exponents represented in the bias notation. So this will be the final exponent E. And then what we will do is we'll compute temporary value W, which is the product of the significance. So the same way multiplied 4.0 times 5.0. So whatever are the significance, we'll multiply them. After that, we need to normalize it in the sense that if the significant is greater than or equal to 2, then what we need to do is that we need to shift the number to the right and and also adjust the decimal point. So this normalization has to be done to ensure that all our numbers are in the normal form. Then if some shifting has been done, some amount of rounding can be done. Not can be done, has to be done, because if some bits are being thrown out, we want the remaining significant to reflect their effect at least. Rounding can cause further problems, so we have to renormalize. So mind you, these steps are exactly the same as floating point addition and subtraction. So they are exactly the same as we had in floating point addition and subtraction. So I'm not, rediscussing them. All these steps remain the same. The only steps that are different is that we add the exponents, and since we would be adding the exponents in a biased form, we'll be essentially adding the bias twice. So the bias, at least one of them, needs to be subtracted. Second, we need to multiply the significance, and the rest of the stages remain the same. So the complexity of this is same as the time taken is the same as the time for an add subtract, and multiply, which is all in log n time. Then one more thing that I didn't mention is the sign of the result. So if both the numbers have the same sign, the sign of the result is positive. So, and if both of the numbers have opposite sign, the sign of the result is negative. So once we have the sign of the result, we have the new significant which has been normalized and the new exponent. We can construct the result. So we can given two floating point numbers with a multiply operation, we can construct the result and we can return it. Alright, so let me now summarize the same process, the same procedure with the help of a flowchart. So let's assume that we are multiplying two floating point numbers a and b, and the product of the numbers will be saved in C. So if a is, so first let us do some very simple checks. If a is equal to 0, then we can set C to 0 and we can get out. Else if b is equal to 0, we can set C to 0 and we can get out. Otherwise, some amount of additional work is required. So let's see what's the additional work like. Sorry, this is an extra step that needs to be removed. So the first thing that we do is we compute the sign of the result. So what we essentially do is that we'll compute the sign of the result here, and the sign of the result is an exclusive OR of the signs of A and B. So if both of them have the same sign, right, then so basically the way that we are representing the sign of A or B is by the sign bit. So if the sign is 0, means that the number is greater than or equal to 0. If the sign bit is 1, it means that the number is less than 0. See, as you can see, if both the numbers have the same sign, their exclusive OR is 0, so the number is positive. If they have different signs, the exclusive OR is 1 and the number is negative. So the sign bit is 1. Then we compute the final exponent E, which is EA plus EB minus the bias. And after that, we see if there is an overflow or underflow, because we are increasing the exponent. So if we have exceeded the range of the number system, we report this and we exit. Otherwise, we multiply the significance PA times PB and save it in W. We normalize W and update the exponent. Again, there is a possibility of overflow or underflow. If that is the case, we report. Otherwise, we do some rounding. Then we renormalize and update the exponent. Then if there is, then again there is a possibility of us exceeding the range of the number system. If that has happened, we report. Otherwise, we move to constructing the result. So given the new significant, given the new exponent, and the computed sign bit, we can combine all of these three pieces of information to create the result or the product C, which should be returned. So which is pretty much the output of this particular circuit. Now let us take a look at floating point division. Let's first take a look at a simple division algorithm. So let us divide A by B to produce C. So the first difference between floating point division and regular integer division is that in floating point division there is no notion of a remainder. There is nothing called a remainder in floating point division, because in integer division we had a remainder. The reason was that our quotient could only be an integer. But in floating point division, the quotient can be a floating point itself, so there is no notion of a remainder. This makes our job easy. After this, let's try to design a very simple division algorithm The same way we have division in decimal. So in decimal, let's say that we want to divide two numbers. So what we do is that, so we can, let's say, consider an example. Let's try to divide 4 divided by, uh, let's see, instead of 4, let me make it 5. So what we do is that we will first divide the significance. So 5 divided by 2 is 2.5. Then what we will do is we will adjust, so we'll basically compute the new exponent, which is 10 to the power 5 minus 3. So in multiplication, we add the exponents, in division, we subtract the exponents. So what we get is 2.5 times 10 to the power 2. So this is exactly what we need to do in division. We need to subtract the exponents and we need to divide the significance. After that, the rest of the steps will be the same. So let's first take a look at subtracting the exponents. So let xa and xb be the real exponents. So they are represented in their biased form. So what we need to do is, if you are dividing a by b, we need to compute xa minus xb. Since they are being stored in the biased form, they will be stored as xa minus xb plus bias. So recall that EA is XA plus bias. Similarly, EB is XB plus bias, plus the bias, right? So EA minus EB is same as XA minus XB because the bias gets cancelled out. That's the reason we need to add the bias once again to the result of the subtraction to compute the final exponent, which is saved in biased form. Alright, so what do we do once again? Sorry, we extract the exponent field from A and B, we subtract them, and then we add the bias. So why do we add the bias? The reason we add the bias is because the E fields are essentially stored in bias notation themselves, and they are basically equal to the real exponent plus the bias. Alright? So once I subtract EA minus EB, the bias gets subtracted. But since the final E field also needs to be saved in bias notation, we need to add the bias once again, such that what we are essentially encoding is XA minus XB plus the bias. Subsequently, what we do over here is that we divide the significance. So we divide PA by PB, and we save that in the result W. Right, so E and the W is the standard convention that we have been using up till now. After this, what we do is we normalize the result that we have to do. If some bits were discarded, we do some rounding, and then we renormalize. So these three steps will always be common in all floating point algorithms. It's not just addition or subtraction, it's also multiplication, division, and anything else, that the final output has to be normalized. After that, if some bits are being discarded, there's a need for rounding. And if that again causes the number to be in a non-normal form, it needs to be renormalized once again. And in the book, you'll find a proof that renormalizing only once is sufficient. You don't have to renormalize twice. All right. So I'll not discuss the specifics, but it's just that these three steps will be common in all algorithms. So what is the complexity of this? Okay, so the complexity of this entire algorithm is same as the complexity of the division here, which is the most complicated operation. And what we have seen is we have seen two algorithms for integer division. So mind you, this division is an integer division, and we have seen two algorithms for integer division, and they take order of n log n time, right? So this is yeah. So basically here they take order of n log n time. So actually, in this case, it's not exactly integer division, because when you're dividing 5 by 2 to get 2.5, you're not doing integer division. Rather, what you're doing is that you're dividing 50 divided by 2. So then you're getting 25. And then you're putting the decimal point between 2 and 5. So this is what we have learned in our primary school, that to divide, let's say, one number by another, to increase the precision, we can left shift the dividend by certain positions, and then right shift the final quotient, right? So that will give us the floating point division. But essentially what we are doing is we are dividing numbers, albeit we are increasing the precision by first left shifting the dividend and then right shifting the quotient, right? The same way that we divide two numbers to get a decimal output, the same primary school algorithm, that can be done. But in any case, the integer division algorithms that we have learnt take order of n log n time, so they are slow. So it turns out that we can design algorithms which are much faster and which are better in terms of their properties. So let's look at them next. But the summary of this particular slide is that the final result is pretty much coming out of a process of division, and this is the slowest operation because we are essentially using integer division, albeit in a slightly different fashion. And so that's the reason. But anyway, this is a slow operation, takes n log n time, using both the restoring and non-restoring algorithms. That's the reason the overall algorithm is slow. And what is the slightly different fashion? So let's see, if I want to divide 5 by 2, I can always say that, look, the quotient is equal to 2. It's regular integer division. But what we have learnt in school, in primary school, is slightly different. If I want to divide 5 by 2, what I actually end up doing is I divide 50 by 2. So I get 25. Then I realize that since I had multiplied 5 by 10, uh, I'll sort of compensate for that. So if 50 by 2 is 25, I'll say that 5 by 2 is 2.5. And let's see, if I want more precision, so I want to divide 5 by 3. What I can instead do, if I need more precision in the output, is that I will first compute what is 500 by 3. So 500 by 3 in regular integer division is 166. So I'll say that, look, since 500 by 3 is 166, 5 by 3 is 166 divided by 100, which is 1.66. So similarly, instead of 500 by 3, I could have done 5000 by 3, and then or I could have done 50,000 divided by 3. So this would have given me 16,666. Then I could have said that, look, now 5 by 3 is 1.6666. So I've increased the number of digits after the decimal points. I've increased the precision of the result. So, but what I'm doing in each and every step is regular integer division. So I am first computing the result of one more division where the dividend has been shifted to the left, and then to compute 5 by 3, I'm inserting the decimal point at the right and appropriate location. So the same thing can be done over here. This is not regular integer division. I can shift, let's say, the significand of A by certain places to the left, perform the division, and then shift the quotient that many places to the right. So that has not been mentioned to avoid cluttering up the slide, but this is pretty much what I would do. What I do anyway for normal division, right? Normal primary school division, that also can be done. But in any case, the long and short of it is that this is a slow operation. So I can do something which will make all my operations much faster. So let us look at Goldschmidt division. So we'll talk about two division algorithms. So one is Goldschmidt division. So my basic uh, insight is like this. Let's say I want to compute A divided by B. So A divided by B is A multiplied with 1 by B. I have a fast algorithm for multiplication. So pretty much my problem reduces to finding what is 1 by B. So 1 by B is known as the reciprocal. So if I have a fast algorithm for finding the reciprocal of a number, then what I can do is I can multiply that, multiply 1 by B with A and compute A by B. So let us thus try to compute the reciprocal of B, which is 1 by B. Then we can use standard multiplication. Also, if B is represented in the normal form, which is PB times 2 to the power x, which is the exponent, then I can compute 1 by PB, I mean 1 by the significand times 2 raised to the power minus x. So this part is simple, this can be ignored. So I can just take the significand and try to compute 1 by PB, which is the core part of the operation. So let's first consider the case of a normal floating point number. And of course, if B is a denormal number, we can do something similar. But I will not, discuss that in the interest of time. But a very, very easy extension can be done to handle denormal numbers as well. So let me just consider the case of normal significance, where a normal floating point significand is between 1 and 2, in the sense that 1 is less than equal to PB, which is less than 2. So if this is the case, I can represent the floating point significand PB as 1 plus x. So 1 plus x where x is less than 1. So this is so PB is between 1 and 2. So since I can thus represent it as something as the form 1 plus x, where 0 is less than equal to x and x itself is less than 1. So this can be done. Given the fact that this can be done, let us now do some more algebra. So the algebra that we will do is like this, that the first thing that we will do is that we'll slightly clean up one special case. So we have said that 0 is less than equal to x is less than 1. But look at what happens when x is equal to 0. So when x is equal to 0, then the significand is essentially 1. If the significand is 1, the reciprocal of the significand is also 1. So this is a very trivial case and this can be handled separately. So at least in this discussion, let's assume that the significand is of the form PB equals 1 plus x and 0 is less than x is less than 1. So x is strictly between 0 and 1. It'll make our life simple. Then let's go to the next step, which is let's say that x is of the form 1 minus x dash, or alternatively x dash is of the form 1 minus x. So since x is strictly between 0 and 1, also x dash is strictly between 0 and 1. So we can say that x dash is less than 1. So some more algebra, 1 plus 1 is 2. So this is 1 by 2 minus x dash. I take the half outside. Then I have 1 divided by 1 minus x dash by 2. So this is half times 1 by 1 minus y, where I say that y is equal to x dash by 2. So this term is being represented as y. Since x dash is less than 1, y is less than half. Alright, so since x dash is less than 1 and y is equal to x dash by 2, y becomes less than half. So we finally end up with this expression over here, when 1 by the significand is half times a number of the form 1 by 1 minus y, where y is equal to x dash by 2, which is equal to 1 minus x divided by 2, which can be computed very easily, right, using a regular subtraction and a shift, right, and a right shift. It can be computed very, very easily. Alright, so what we can do is that actually let me go back. So since we are multiplying a number by half and everything is in base 2, so multiplying a number by half pretty much means multiplying a number with 2 raised to the power minus 1, or dividing by the number by 2 is that we will compute the result of 1 by 1 minus y and right shift it by one position. So that is the same as multiplying it by half. So for example, 6 divided by 2 or 6 times half, 6 is 110. This if I'm dividing by 2, it's the same as right shifting this by one position. So the result is 1 which is 3. So this half is not a big deal. Even multiplying a binary number with half is same as right shifting. That's also not a big deal. The difficulty lies in computing 1 by 1 minus y. If we can do that quickly, we are done. So 1 by 1 minus y is equal to, let's see. So let us multiply 1 plus y to the top to the numerator and 1 plus y to the denominator. So we get 1 plus y, and recall that 1 minus y times 1 plus y is 1 minus y square. So similarly we can do the same once again. So we can multiply 1 plus y square to the top. So, and if we multiply 1 plus y square also to the bottom, so we can basically do this. If we multiply 1 plus y square to the bottom as well, so 1 minus y square times 1 plus y square is 1 minus y to the power 4. So we can continue in that way. So then what we will see is that we'll have the numerator will be 1 plus y square till 1 plus y to the power 16. And the denominator will be 1 minus y to the power 32. So here is an interesting observation that we can make. Given the fact that we are working with a 32-bit system where the mantissa has only 23 bits, right? Given that, that's a fact for us, irrespective of the value of y, right? So what do we know about y, right? Instead of saying irrespective of the value, let's see what do we know about y. Let's go to the previous slide. What we know is y is less than half, right? This is something that we know, that y is less than 2 raised to the power minus 1. So y to the power 32 is less than 2 to the power minus 32. Alright? So if this number is less than 2 raised to the power minus 32, so this is well outside 32 bits. So this y to the power 32 in our system is practically 0. The reason being that it cannot be represented at all within our 23 mantissa bits. Right? So I cannot represent a number 1 minus y to the power 32 where and the reason that's the case is that 2 to the power minus 32 basically means that we have 0. Then we have then we have 31 ones. Sorry, we have 31 zeros, and then we have a 1. So 1 minus this quantity simply cannot be represented using 23 bits. So no valid mantissa can capture or represent this number, because this number is simply, y to the power 32 is too small to be captured in our number system, and 1 minus y to the power 32 is too close to 1, and there is no way of representing this. As a result, there is no point in multiplying this with even more terms, and this term 1 minus y to the power 32 is practically 1, because irrespective of whatever its value is, it cannot be represented, and also it makes no sense to multiply the numerator and denominator with other terms. For example, even if you multiply this with 1 plus y to the power 32, it will make no difference at all. The reason being that y to the power 32 cannot be represented, so it will not affect any of the other terms. Since it will not affect any of the other terms, so this number is approximately equivalent to 1 plus y, 1 plus multiplied with 1 plus y square till 1 plus y to the power 16. So we are actually discarding the denominator. Alright? And the reason we are discarding the denominator is because the denominator is too close to 1. And it is in fact so close that our number system will not be able to distinguish between just the numerator and the numerator divided by the denominator. The reason it will not be able to distinguish is for another reason. So let's consider, one reason we have given. Let's also consider one more reason. So what is, you know, 1 by any number of the form 1 by 1 minus x, right? This is a number of the form so on and so forth, right? So any number of the form 1 by 1 minus is equal to see if I expand the denominator in using this particular series expansion, so the 1 will get multiplied with the numerator, but if any of the other terms get multiplied with the numerator, there will be no way of representing the product because all of those numbers will be less than 2 to the power minus 32 given the fact that y is less than half, and they cannot be represented. So since they cannot be represented, they'll have to be ignored, and that is why we ignore the denominator. And what we have essentially created, maybe I can clean the slide and show, what we have essentially created is we have replaced a fraction with a numerator and a denominator with just a product of terms without a denominator at all. And the product of terms is 1 plus y times 1 plus y square till all the way till 1 plus y to the power 16. Alright? So this is exactly what we have done. It's a product. And this can be very quickly computed in our system. So what we can do is first we can compute y. Then we can compute y times y, which is y square. Then we compute y square times y square, which is y to the power 4. We do the same to get y to the power 8, and then we do the same to get y to the power 16. So this is 5 steps. So if it's an n-bit number system, this will take log n steps, where in every step there is a multiplication. That again takes log n steps. So total complexity is log n square. So this is significantly faster than the n log n time algorithm that we have seen. And the reason it is faster is because we pretty much use this expansion over here. Right? This kind of an expansion is used. Alright, so using this particular form, we have been able to quickly compute 1 by 1 minus y. Right? So 1 by 1 minus y is pretty much a product of terms of the form 1 plus y square times 1 plus y to the power 4 times 1 plus y to the power 8 times 1 plus y to the power 16. So pretty much is a product of 5 terms. For each term we compute a power of y. So we compute the product of these 5 terms, and this is our result. Once we have 1 by 1 minus y, we need to multiply it with half, which is the same as right shifting it by 1 position. So this will give us the reciprocal of the significand. Then we again go back, and given the reciprocal of the significand, we'll multiply it, with the significand of a. So we basically get PA divided by PB, and then the rest of the division algorithm will be the same as. So we are essentially getting this point, albeit with a much faster method. The rest of the steps are exactly the same. All right. So the complexity of this, I'm sorry, there's a small error in this slide. So time complexity of finding the reciprocal is log of n square, right? As we had computed on the last slide, that is log of n square. And the time required thus for all the multiplications is log of n square, and the total time is log of n square. Sorry, this is one bug that I'll fix in the subsequent versions of this slide, but this is what it should be. Alright, so let us now use a slightly different kind of method to find the reciprocal of PB using the using a different method called the Newton-Raphson method. So Newton-Raphson and Goldschmidt are similar methods, but let's at least for the sake of it learn a new method. So given any number, let's try to find the reciprocal of the number. So let us designate PB as a generic number B, where B is of the same range, 1 is less than equal to B, which is less than 2. So the aim is to compute 1 by B. So let us do one thing. Let us create a function fx where fx is equal to 1 by x minus b. Right? So let us arbitrarily create a function fx of the form 1 by x minus b. Right? So fx is equal to 0 when x is equal to 1 by b. What we can say that when fx is equal to 0, right? So that is when 1 by x is equal to b, or rather b, x is equal to 1 by b. So we have created a function of this type. So the problem of computing the reciprocal, right? So the reciprocal of b is the same as computing the root of fx. So the root of fx is where fx becomes 0. And where does fx become 0? Well, fx becomes 0 when x is equal to 1 by b. See, if I can take this equation and find the point where it becomes 0, then essentially I'll find that point is where x is equal to 1 by b, and that is the reciprocal which we want to compute, right? So I'm essentially, what I'm doing is I'm converting the problem of computing a reciprocal 1 by some number as computing the root of an equation. So we'll use a traditional equation solving technique to actually compute the reciprocal of a number. And this technique is the Newton-Raphson method. So let us do one thing. Let's start with an arbitrary value of x, which is x0, right? So let us guess a value, arbitrary value, and start from there. Let us locate x0 on the graph of fx. Let us draw a tangent to fx at this point, and let's keep repeating. So a picture is worth 1,000 words, so I'll tell you what we do. Let us arbitrarily guess a value of x, which is x0, right? And then we locate the point x0 on the curve of fx. So this is the curve of fx. Let's assume that for some fx this is the curve. So what we will do is that at this point, let us compute a tangent to this curve. So if we compute a tangent to this curve, at some point this will intersect the x-axis. So let this point be x1. Again, let us locate the point on the curve y equals fx, where its x coordinate is x1, which is this point. Let us again compute a tangent to the curve. So let it intersect the x-axis at point x2. Let us again locate the point on fx, whose x coordinate is x2. Again we compute the tangent of the curve, and let this point be x3. So in this manner, we just can keep going till we reach the final root, and the root is where we expect x to be equal to 1 by b. The standard equation solution method is called the Newton-Raphson method. And so here it's a mathematical method where we take some point on the curve, we keep computing tangents, till we hit the root. So the way that we would actually do it in hardware is that we'll implement this maths in the hardware. We'll start from a random point x0, find the point on the curve, compute the tangent, see where it intersects the x-axis, again find the curve and keep repeating the process. So recall that my equation was fx is equal to 1 by x minus b. So computing the tangent means finding the derivative at x, right, at some point x, wherever we want to compute the tangent at. So f dash of x is dfx by dx, which in this case is minus 1 by x square. So at x0, the derivative of the curve is minus 1 divided by x0 square. So the equation of the tangent, so let's find the equation of tangent. So let's say the equation, a general equation of a straight line, y equals mx plus c. So in this case, we know m, which is the slope. The slope at x0 is minus 1 by x0 square. So essentially the equation of the tangent is y equals minus x by x0 square plus a constant c. So we need to now find the constant c. So what do we know? We know that at x0, y is equal to, right, the value of y, which is equal to fx, is equal to 1 by x0 minus b. So this is something that we know because at x0, fx is 1 by x0 minus b. So this is something that we know. This can be substituted in this equation to find the value of c. So once we do that, what we see is y equals, right, mx plus c. So at x0, this is the value of y, 1 by x0 minus b. Mx, so this part was m minus 1 by x0 square. And at x0, the value of x is x0, of course, plus c, which is the constant whose value we want to find out. So what we will do is we'll do a little bit more of algebra, and it will come that, the last stage will tell us that c is equal to 2 by x0 minus b. So the equation of the tangent becomes y equals minus x by x0 square. So the equation of the tangent, of course, you can say at x0, right? So this is something that can be said, that the equation of the tangent at x0 is y equals minus x divided by x0 square plus 2 by x0 minus b, right? Mx plus c, we know m and c, so this is the equation. So let this tangent, this line, intersect the x-axis at point x1. If that is the case, what we can do is, so we need to find this point x1. So what we know is that when it intersects the x-axis, y is equal to 0. So we can thus say that 0, and this needs to be mx plus c. So since we have computed this as the value of c, and this is the value of m, the value of x where this intersects the x-axis is x1. So this is the equation that we can create, and if we solve this equation, we'll find that x1 is equal to 2x0 minus bx0 whole square. So let us now define one more function called an error function. So recall that we have defined two functions arbitrarily, we have guessed, and we hope that it will help us. One such function that we had defined is fx, which is 1 by x minus b. So the insight here was that at the root of the function, when fx is 0, we will have x as 1 by b, which is what we want to compute. Now we are guessing one more function called the error function. So the error function is defined as like this. So these functions, defining them is actually an art. For different functions, you need to define them differently. So in this case, this is how we are defining them. So the error function ex is bx minus 1. That's the way we are defining it. So what is the advantage of defining it this way? That when we reach the root x, where x is equal to 1 by b, the error becomes equal to 0. So you just put x here. So if x is 1 by b, b times 1 by b is 1, and 1 minus 1 is 0. So the error is 0. So our aim is also to make the error as 0. And the error happens to be 0 when we reach the root of the function fx. So what is the initial error? So the initial error at point x0 is bx0 minus 1. That is the initial error. What is the error after we reach point x1 is bx1 minus 1. Since this is what x1 was computed to be, if we go back, we'll say x1 was computed to be this expression. So bx1 minus 1 is b times 2x0 minus bx0 whole square minus 1. We do a little bit of algebraic manipulations till we come to this result. So so the error is minus of bx0 minus 1 square, and bx0 minus 1 is the error of x0. So this will become minus of error of x0 square. So we can alternatively say that the error at point x1, its absolute value is equal to the absolute value of the error is equal to the square of the absolute value of the error at x0. Similarly, we can extend this argument. We can say that the error, sorry, we can say that the error at any point xn is equal to the error at x of n minus 1 square, which is equal to the error at x of n minus t to the power 4 and so on. So we will use this result. The way we will use this result is like this, that let us now try to put a bound on the error. So we know that since b is actually representing the significand of one of our floating point operands, it is between 1 and 2. So 1 is less than equal to b is less than 2 is the significand of a normal floating point number. So let our first guess x0, right? Our first guess x0 actually be half, right? So the range of bx0 minus 1, b times x0 minus 1, what will it be? So what is the range of b? B is between 1 and 2. So the range will actually be between minus half and 0, right? So that will be the range of bx0 minus 1, which is the error at point x0. So hence ex0, the error at point x0 is always less than equal to half. Since the error at any point is less than equal to half, and we reduce the error by a power of 2, in every iteration, ultimately the error will approach 0. Because if we come back to this equation, then initially if the error, is half, then at this point the error will be 1/4, and this will become 1/8, and it will sort of keep going down and down and down till it ultimately reaches 0. Right? So because any number that if we multiply by itself and the number is less than 1, it will ultimately reach 0. So the error will ultimately converge at 0. So this at least tells us that our initial estimate, if we set x0 as half, is a good estimate, because we can not only bound the error, but we can, in repeated steps, the error will ultimately converge to 0. So let us look at the maximum error that is possible in iteration 0. In iteration 0 it is half. In iteration 1 it's 1 by 2 square. 2 it is 1 by 2 to the power 4. 3 it is 1 by 2 to the power 8. 4 it's 1 by 2 raised to the power 16, and ultimately 5 is 1 by 2 raised to the power 32. So one thing that needs to be kept in mind, that the error after 5 iterations becomes 1 by 2 to the power 32, which is a fairly small number. But there is a very, very important point to make here, that the error function that we actually considered, which is, let me go back. The error function that we actually considered here, I had at that point said it's defined arbitrarily. Now let me take some liberty to say that it was not that arbitrary. It has a certain physical connotation, and this physical connotation we'll require right now. So why don't you remember this expression and carry on with me till this slide. So we had said that, look, the error function ex is defined as bx minus 1, which is essentially b times x minus 1 by b. So x minus 1 by b is pretty much the distance between our current estimate of what the root is and the theoretical root, right? So this is our current estimate, that is x minus 1 by b. Right, so that is essentially the difference between what we want to compute 1 by b and what we currently have. So basically you can say that this is b times delta, where delta is the difference. So if b times delta is, let's say, equal to 2 to the power minus 32, and b itself is a number. So what was the bound on b again? The bound of b was between 1 and 2. So b itself, if it is between 1 and 2, it means that delta is definitely, the bound on delta. So let's say if this is 1, this remains. If this is 2, then delta will be a number between 2 to the power minus 32 and 2 to the power minus 33, which is anyway much smaller than what our mantisas can represent, because our mantisas cannot go beyond 23 bits. So 5 iterations is more than enough to drive the delta. So delta here is defined as the difference between what we have and what is the ideal value, right? So this delta over here, 5 iterations is sufficient to drive the delta so low that it is beyond our limit of precision, so thus we should not be concerned. Which further means that if we do the Newton-Raphson iteration for 5 iterations, whatever value of x that we have, see initially we have x0, then we'll have x1, finally we'll have x5. The value of x5 is very, very close to the value 1 by b, which is what we wanted to compute. So there is still a small difference, and this difference is delta, but the difference is smaller than our smallest precision. So, and since this floating point representation is approximate, we can use this fact to, in a sense, ignore that minimal amount of error because there is nothing that we can do about it and go forward. And why are we ignoring? Because our mantissa has a fixed size, which is 23 bits, right? So that's the reason there is no choice. All right. Now, given the fact that we have put a limit or bounds on the error, what we thus see from this slide is that 5 iterations will suffice. And why 5? Because we reach to the power 32, which is beyond our uh, beyond our limit of 23 bits. So how many iterations do we take? Well, if we have a 32-bit number system, so in that sense n is equal to 32, and we proceed in powers of 2, so we proceed in log steps, so we require log n iterations. And in each iteration, what do? We compute a new value of x. So what is the new value of x? The way we compute it is x1 is equal to 2x0 minus bx0 square, or alternatively any xn is 2 times x n minus 1 minus b x n minus 1 square. So there are only multiplications and subtractions here. So each step also takes log n time. So the total time taken by all the steps is log n times log n, which is log n whole square, order of log n whole square. So this takes exactly the same amount of time as the Goldschmidt algorithm. It's just a different way of doing things. It has a certain graphical connotation. And one more interesting thing that this can do is that, of course, we used it to compute the reciprocal. But we can use it to compute other mathematical functions also. But this I'll mention after a few slides. All right, so the time complexity is like this. Again, a small error in this slide, I'll fix it. In every step of the operation, we need to compute this thing. So this requires some shifts and multiplies and subtracts. So this requires order of log n time. So the total time of the algorithm, sorry, a small mistake here, is order of log n for each step multiplied with log n steps, right? Which is order of log of n square. Like log n whole square. Alright, so this is the time. So it's same as the Goldschmidt algorithm in that sense. Alright, so we reach the end of the chapter on computer arithmetic, a fairly large chapter. So I leave you with a problem to do. Can you use the Newton-Raphson method to design a piece of hardware, a hardware circuit, to compute square root of x? So given a number, we want to, given a positive number, we want to compute its square root. So for this, you need to find two estimates. One estimate for fx such that its root is equal to square root of x, and another error function such that it has some physical connotation with the actual error, and also the error function reduces significantly in each iteration, such that the number of iterations are bounded and ultimately the error approaches 0. So you need to guess these two functions, do a little bit of math, the rest remains the same, And at the end, you need to give us a fast hardware algorithm to compute square root of x. Alright, so this ends chapter 7. I'll see you in chapter 8 where we'll discuss processor design.